Okay, so good morning everybody, I hope you're doing great today. According to our plan, our lecture today will be divided into two parts. The first part will be the proper lecture presentation, and then the second part will be dedicated to some questions that you might have before the exam, and I'll say also a few things about the exam. I sent you emails about it already, but we can elaborate on this a little bit, right? So let's do this. Okay, so all right. So what we did last time, we looked at good morning. We looked at the second order perturbation theory correction to the energy. In order to do this, we introduced a diagrammatic representation for our one and two body perturbation operators. As you remember, perturbation operator consists of one and two body pieces. The one body piece is Qn. Okay, this new operator called Qn, which is the difference between Gn and Un, where Gn is the one body operator that originates from normal ordering for the V, and Un is the one body operator that we propose to use in perturbation theory to build the unperturbed Hamiltonian. Okay, and then so maybe I'll write it this way, this is W1. Then the two-body part of our perturbation operator is simply the normal ordered form of the V operator that we have in the true Hamiltonian. And as I said, so the W2 is of course the real interaction, whereas W1 is a consequence of us using an operator U that may not be identical to G. In other words, it's also this operator measures the deviation between the Fock operator and the Zn plus Un, which is, as you remember, the unperturbed Hamiltonian. Okay, so if you deviate significantly from the Fock operator in your zero-order description, then of course you're going to see significant contributions, potentially significant contributions from this operator Q. Okay, but on the other hand, if you use the Hartree-Fock reference, then operator Q is 0, then the whole theory simplifies greatly. We just have to deal with Vn. Okay, and then so what we did, we introduced a diagrammatic representation in a usual way. So for W1, we decided to use a vertex which has a little triangle hanging at it. That would be a Hugenholtz form. So I'll put H here, or the Goldstone form. Okay, so I'm going to put a G here for the Goldstone. Okay, and then for W2, of course, we rely on our well-known already to us representation, where this is the Hugenholtz vertex, and then for the Goldstone we have a super vertex consisting of two simple vertices. Okay, so again, Hugenholtz, Goldstone, and then we also discussed the diagram representing the reduced resolvent, because we needed it in perturbation theory. So we discussed diagrams representing the kth body, the kth power in general, where k can be as little as 1 and as big as really, well, the number of fermions in principle. Then we have here the n-body components of it. And the diagram, we decided, after some analysis, that the proper representation for this operator could be something like this. We have lines that are going through this sort of rectangular shape. Okay. So we have, say, let me actually put labels here. I didn't put them there because they're obvious. So A1, I1, AN, IN here, and the same indices on the right side of our diagram. Okay, and then we're slicing this diagram through. Okay, and we're hanging the sort of circle that reminds us what is the power of the resolvent. And the way we read it is that we have this line tells us that there is a projection operator. The excitation phi0 excitation. Okay, and it also brings us information about perturbative denominator, which you read by simply subtracting single particle energies of the particles from the single particle energies of the holes, okay, raised to the power k, which is indicated here, okay. And with this sort of schematics, we started analyzing the second order contribution to the energy, K02. Okay, we ended up, which is actually defined formally as phi 0 perturbation resolvent perturbation phi 0. As you remember, since W is a sum of 1 and 2 body pieces, or Qn and Vn, then we could split it into 4 pieces. Okay, phi 0 Qn resolvent Qn phi 0 plus phi 0 Qn resolvent Vn phi 0 plus phi 0 Vn resolvent Qn phi 0, and plus the fourth contribution, which consists of Vn operators only. I feel that I need to fix my shoe. Apologize for this. And we, by simply drawing resulting diagrams corresponding to two perturbation operators, Q's or V's, and the resultant in the middle, we showed that the middle two parts, this one and this one, vanish, and we're just left with those, the first and the last. Okay? For the first one, we ended up with a diagram which looks like this. Okay, with triangles hanging out here. Slice through, okay? And then we label it, put in A and I here, A and I here, okay? Which we read, okay, obtaining a sum over A and I, Q, A, Q, I, over epsilon I minus epsilon A. So the IQA and AQI, those are read straight from the Q vertices, and the denominator is read from slicing the lines. You know, that's the resolvent contribution to it. That's what we obtained. And then for the two, for the last term, we obtained. Maybe I'll try to squeeze it here. We obtained a diagram that, in a Hugenholz form, looks like that. We have 4 lines passing through the resolvent, 4 lines connecting the V vertices. So A, I, B, J, A, I, B, J, okay, which once again we read. Of course, we had to write the corresponding random, all right, and we obtained the expression 1 over 4 sum over A, B, I, J, that would be I, J, V, A, B, anti-symmetrized, times A, B, V, I, J, anti-symmetrized, divided by the denominator associated with, again, slicing the diagram in the middle, okay? So we obtain epsilon I minus epsilon A plus epsilon J minus epsilon B. And I think this was, it was the final expression, right, of our final equation of our previous class, okay? So we demonstrated that the second order correction to the energy is the sum of these two terms, okay? And I'll come back to their analysis when I say a little bit more about the rules of the MBPT diagrammatics, okay? Well, first of all, maybe just a little comment. We did all of this at the level of Hugenholz, you know, so this was, of course, here there's no difference, but here there is, right? We use Hugenholz representation. That means that we also had to produce the corresponding random diagram, and we worked it through, okay? But of course, you know, if you chose to use Goldstone representation, and as you know, it is useful when you want to, for example, spin adapt your expressions, okay? Then, of course, you know, this analysis would be very similar. So I just show that if we use a Goldstone representation, maybe just one example to comment on this. Okay, and as an example, I'll take what we used to call, I think, the D contribution. which is the last one there, VNR0, VNP0. So what will happen in this case? Well, you would start the same way as you normally start. You would have Vn vertices on both sides of the resolvent. Okay? And in the middle you will have a resolvent. Of course, initially you don't know which part of it, so you have to assume that you have to consider all of them, that is all many-body components of it. Okay? So I'm really following the recipe we tried to work out last time. So we have these lines, particles and holes. Okay? So A1, I1, AN, IN, A1, IN, I1, AN, IN. We're slicing through. We have the first power of the resolvent, so we're hanging the circle with one inside it. Okay? Well, then we have to bracket this with Phi0. Okay? On both sides, because that's what our expression requires. And then we have to sum it over n. Okay? From 1 to n. Okay? That's how you would start the Goldstone diagrammatics. And as you can see, once again, following the same consideration that we did before, remember the middle part, that line here, has a projection operator. It has this element right in the middle. I'm not going to write the whole thing. I just say that it has Phi0, where the dashed line sits. Okay, that tells us that we have to contract all the lines between these two Phi0s. Okay, so in this region of the diagram, to the left of the dashed line, we have to have full contraction. So I'm going to say fully contracted. And the same happens in the right region of it, between this line and that, we would have to fully contract. Okay? And that means that n would drop to 2, okay, like we said last time. So that because you have 4 lines here, 4 lines here. So in order to produce diagrams with no external lines in both regions, the left and the right, n would have to be 2. So after working this out, you would immediately end up with the following 2 diagrams. Okay, so the first diagram would be, and I'm sure they're all familiar to you, at least based on our experiences with drawing diagrams for multiple V vertices. We did this already. You actually have homeworks about it even, right? So we've seen it many times. So one diagram would be like this. That would be a first Goldstone. Okay, and let me label it A, I, B, J. Remember that A line passes through. So you have to use the same A here, the same I here, same B here, same J here that you have on the other side, because that's how this whole diagrammatics works, okay? And then the other diagram that you would obtain, would look as follows. Okay, you would say, let's do it like this. I would start with A going here, then you pass it through, okay? You end up here. But instead of returning back on the same loop, you would go down, okay, say on the I line, all right, and then you would pass through, and you would end up here, okay, and then you would return back on this line, let's call it B, pass through the diagram on the B, okay, and then return to the bottom simple vertex, okay, and then you leave the bottom vertex with, say, a line that we're going to call J. It's a whole line, okay, going to the right. You end up somewhere here, pass through, and return here. Okay, of course, this is all connected. Right? So we have here J. So that's the diagram you would obtain. It doesn't look very pretty, okay? We're not going to be drawing this too many times anymore, okay? Don't worry about it. This is just to illustrate what I'm doing. And then you would read them. So the only reason I showed it to you, I wanted to show you that this denominator rule that we're developing, right, seems to be works also for Goldstones. So how would you read this diagram? Okay? Well, this diagram, let's start with the weight of it. So the weight of this diagram, you can think, of course, that there are 2 loops still. So that's the kind of thing you see, right? So you would say that it's 1/2. But I can give you another argument. You remember when I started advocating this form of the resolvent, okay? I mean, when I was sort of working towards this representation, I said that this picture is really produced from something that looked like this. Okay, let me just remind you there was this fake diagram obtained from simple vertices. Okay? Try to hopefully squeeze it here. Okay, then really, if you think about what is the resolvent, sort of the middle part of it, that part. Okay? That's really something like that. You remember, that was the sort of thing that we used as a precursor of our diagrammatics involving resolvents. Okay? Okay, I'm not going to put labels, you know that, well, I can, of course, this is A, I, B, J, and here also A, I, B, J, okay? So that's how we started with the resolvent, and we said, well, that's a little bit too complicated, so let's just redraw it in this sort of form like this, right? But it's useful to, look at this again, because this is really the Goldstone representation of the resolvent. And now if you kind of, I'm not going to redraw this with this, okay? This is going to get a little bit out of control for a time. But if I put this over there, okay, you can see that what you will really see is the following. You have this is one loop, it ends up here. That's another loop that ends up there, okay? The BJ lines will connect and kind of close here, okay? Like close here. Okay, so there will be 2 loops on the left, 2 loops on the right. And you may think, wait, you have 4 loops now. So it looks like the weight factor should be 1/4. No. Not here. Because indices AI here and AI here are the same. So you cannot just flip these two without watching what happens on the other side of the resolvent, okay? In other words, if I connect these, this vertex here to this one loop here, one loop here, if I decide to look at transformations, so I flip them, I have to flip those two at the same time. Okay, because these indices go through the resolvent. So they're not independent in that sense. Okay, that's why weight in the Goldstone representation is 1/2. Okay? And similar would happen here. And for the sign, the counting of the sign is a little bit different, because if you think about this representation of the resolvent, then how many loops we've got? Not 2, but we have 1 for this, another one for that, 3 and 4. So we have actually 4 loops and 4 internal whole lines. In Goldstone, so if you want to insist on Goldstone and keep all these diagrams in it, right? Because you have I, J, those are 2 internal lines here, and I, J, 2 internal lines here, so altogether there are 4 of them. Which means that the sign is -1 to 4 plus 4. Well, it happens to be +1, so you're fine. Okay, and if you look at the bottom Goldstone diagram, well, in this case, the number of loops is 2 on the left, because, they're closing right here, okay? But there's 1 on this side. Okay, so the number of loops is actually 3. The number of internal lines is still 4. Okay, so you end up with a sign which is -1 to the 3 plus 4, which is -1. Okay, so you see, we're getting these signs in a different way. If I didn't look at this sort of, what is the internal structure of the resolvent, I would count it differently, but I would still get the same phase factors. Okay, because the parity, so to speak, is preserved. Okay, so that's all. But then once again, if you read these diagrams, well, let's actually do this. So what do we obtain for this term? K0, 2 with a D. Okay? Well, we obtain, 1/2. We have a sum over A, B, I, J. Okay? And then we're going to have the following. For the first diagram, we have, outgoing IJ, V, incoming AB to the left vertex. They're not non-symmetric because we're talking about Goldstone. And then we have AB, V, I, J, okay? Divided by epsilon I minus epsilon A plus epsilon J minus epsilon B, because that's what the resolvent brings, okay? And then you get, from the second diagram, you get the same weight, the same summation, okay? The only difference will be the numerator part. Because on the left, if you really look closely, you have I, J, A, B. Okay, so I can copy it here. I, J, V, A, B. But the right matrix element is different. Now you have A, B, V, and you can see what comes into A, B is J, I. Okay? There's J here. Looks terrible. Okay, now it's better. Okay, so Ji, okay? And then you divide by epsilon I minus epsilon A plus epsilon j minus epsilon b. So you can, I'll close it here. So you can see that this matrix element ijab is common. You can wrap it up together, and you end up with a very nice formula. Okay, ABIJ, and then is in the numerator we have IJVAB, and then you can see here we have ABIJ minus ABJI, which is an anti-symmetrized matrix element. So I can write ABVIJ with a script 8 symbol edit, and then the denominator is of course shared. Not a surprise here at all. So that's what you end up with. So that would be a Goldstone calculation for it, okay? Two comments about it. First of all, just like in the previous cases, we don't need to draw the resolvent, okay? To get these expressions if we agree on some additional rules. So if I go back here, as I said already during the last lecture, this result would be obtained from simply drawing perturbation vertices, okay? So if you, we're here, right? Okay, great, thank you. So, so we would simply start with a diagram like this, no resolvent in it, because that's all you would obtain from two Q vertices if you are asked to draw diagrams with no external lines. But you have to remember that there is a resolvent corresponding to lines between the perturbation vertices. And you read it as the denominator, right? You read simply the presence of these lines as epsilon I minus epsilon A. And here, again, it doesn't look like this resolvent brings a whole lot, it just brings the denominator, so you might as well work with a diagram that would be simply this one, right? Just the one that you would obtain from a straightforward calculation involving two V vertices, forget the resolvent, pretty much, right? So it's labeled it as A, I, B, J, and then remember only that there is a resolvent between the two V's, okay? So stick an additional denominator corresponding to the lines between, okay? So maybe I'll put it up. So that's what we see there. And if you go back to the Goldstone calculation, it's the same thing. I would obtain this result without the resolvent. Okay, I would simply imagine that I redraw these diagrams, but I remove the resolvent, okay, from the picture. So what would be the diagrams? The first one would simply be the very familiar shape for us, okay, which is AIBJ here, okay, and the second diagram, if you just eliminate the resolvent, is the diagram that we also have seen before in a different situation, okay, so it's going to be A, I, so you go A, I goes down, B goes left, and then J goes up to the right, okay? You can see that we would get these two expressions because weight of this diagram, now if you don't see the resolvent, you would say weight is obviously 1/2, okay? You don't have to do this maneuvering I had to do before to see that, okay? And the same thing here. Sign here is obviously +1 because there are two loops and two internal whole lines, okay? Without sort of complicated analysis. Here sign is -1, there is one loop and two internal whole lines. And all you need to accept now is that we also have to slice these lines because there was a resolvent there. So, okay, it didn't evaporate, okay, we just don't want to draw it, okay? And associate the perturbative denominator with the lines you're crossing. That's all, okay, that seems to be emerging. So with all of this, let me move on a little bit and now talk about wave functions. We just have to make sure that we're not lost in this calculation because we'll be analyzing wave function in great amount of detail. That's how linear cluster theorem will be discovered, okay, so we really have to know it. Okay, and I start with an example once again. So our example will be the first order correction to the wave function. Okay, that is the lowest order. As you remember, for energy we didn't look at K0, 1 because, as we said, there is no first order correction to the energy, so nothing to calculate. But there is the first order correction to the wave function, which is the resolvent, formally, acting on the perturbation, acting on P0. Well, in our case, resolvent is Qn plus Vn, so you end up with two terms. Excuse me. Okay? And you can work each one of them out in the same way we did the energy correction. So let's start with the first one. R0, Qn, Phi0. Well, what do we get? Well, we get the following. You know, you start with the resolvent, because we're still sort of in this transition period where we are not 100% perhaps sure if we need it or not. Okay, then we have the Q operator. Okay, well, let's use Goldstone actually this time, just for the sake of doing it. So RS here. Okay, and then we have Phi0. Okay, let's do more for the resolvent. Okay, it's a sum of various many-body components of it. So I'm drawing now the n-body component, same way we did it before. Okay, so it's A1, I1, AN, IN here, and you see the same indices here, A1, I1, AN, IN, and you are slicing them through, okay, to read the denominator. Okay, and then we have to sum this over n from 1 to n. That's how you would start. Okay, resolvent Q Phi0. Okay, and once again we just have to keep in mind all the time. It's my bad here. Okay, we have to keep in mind. Always have to keep in mind that this diagram is not sort of as simple as the other ones. It has the middle part. Okay, which contains the excitation operator E, I1, IN, A1 through AN, and then E, I1, IN, A1, AN, permission joint of it. Okay, so this is an excitation, excited determinant, de-excited determinant on this side. Okay, but Phi0 is sort of the central piece, and then we are dividing this by minus kappa I1, IN, A1, AN. Okay. And of course, there is still, you have to sum this over n. That's what you see here. That's the middle part. That's what I said. Okay, let's actually emphasize this like this. Right? Okay? So once again, we have this region to the right of the red line, okay, where you have to contract all the lines. Okay? So this must be fully contracted because you have Phi0 here, and then you have Phi0 there. And here, you have external lines. Okay? There's nothing on this side to block them, okay? But they are particle hole type lines, okay? So now, if you really think about it once again, the way we did before, we have to then fully contract lines in this region. There are two lines of the Q, nothing on this side, so you have to contract those two to these. That means that n has to be set at 1, okay? And with this, you end up with a diagram, resulting diagram that will be much simpler than what we started with, something like this. Okay, you have A and you have I. Of course, there are summation indices, and there's 1, and you just have to read it. Okay, and when you read it, you end up with a sum over AI. The weight is obviously 1, sign is 1, so there's nothing much to do here. Okay, and we have, matrix element is A, Q, I, divided by this part, which comes from this kappa, which is epsilon I minus epsilon A, because we have a minus here. Okay, so the denominator is epsilon I minus epsilon A, but we're not done. That's not energy expression. That's a wave function expression. So you have to look at the right side. What's on the right side? That's what you have on the right side. Okay? This part. But n is 1, so we are having a single excitation. Okay? We are really having there, x, a dagger, xi, acting on Phi0, which is actually a singly excited determinant. Okay? So it seems like this part of the expression brings us information about singles in the wave function. Okay? That originate from the Q. Not all singles, just those that originate from the Q. Okay? Well, and if I go now to the second part of the correction to the wave function, first order correction to the wave function, part that involves V. Okay, well, once again, you will have to start with the resolvent. Okay, there's a V. I'm going to use Goldstone for, now just, so that you can see that I can use either of these representations, and I'm going to get it right. Maybe I should not go it this way. Let's do it first this way. Not to suggest anything yet, okay? So we are having, again, lines passing through. Okay, A1, I1, AN, AIN, and here you have again A1, I1, AN, IN. Of course, you put some dots in the middle. Put it there. Okay. And slice this whole thing through. All right, and sum over n. Okay, that's how we would start. But once again, for the same reasons that we discussed before, in the middle you have here P0, P0. Okay. Here you have an excitation operator. Here you have a de-excitation form of it, that is a Hermitian adjoint of the E operator. Okay, and again the denominator that resolvent has inside it. Okay, and just like before, we have to make sure that we contract all the lines between this phi0 and that phi0. Okay. So this region of the diagram must be fully closed. Okay, that means that n is 2. You can have 4 lines here, so you have to pick up n equal 2. That's the only thing that survives it. Okay, n equal 1 will not contribute, n equal 3 will not contribute. No singles, no triples, no quadruples, none of this. Just the doubles. Okay, so you end up with a picture that will look at this point like this. Okay, A, I, B, J. Dotted lines. Do that. Okay. Leaving here. So we have A, I, B, J. Okay. And all you need to do now is to read it. Here I'm using a Goldstone representation. So the read of this expression will be right away. You can see that the weight is 1/2, sign is +1, we have no loops whatsoever, okay, or if you count it, okay, let's slice it, make sure I know, okay, please always look, with me sometimes, if I don't copy something, copy it back. Okay, so anyway, we have here the resolvent, so, so you can read it the following way. You have 2 loops, okay, and 2 internal lines. That's the way. One way to read it, that's a plus, or you just think about it being 2 open plus. That's also a plus. So either way, you get a plus, okay? And then you have a summation over A, B, I, J, and the matrix element that you see here is A, B, I, J. So outgoing lines A, B, incoming lines I, J. The perturbation denominator, that's the kappa coming from slicing the lines, is epsilon I minus epsilon A plus epsilon J minus epsilon B. And then we have, this whiteboard is not clean yet. Okay, and then we have the double excitation, okay, operator. So you have XA dagger XI, and you read it from here. You see where it comes from. It comes from the resolvent read now. Okay, so it's X dagger A XI, XB dagger XJ, acting on phi0. Okay, let me rewrite it, squeeze it. XA dagger XI, XB dagger XJ, acting on phi0. Okay, and that of course is a doubly excited determinant, Pijab. So we have doubles in the wave function. Okay, but nothing more. You can see resolvent, all other pieces of the resolvent are out. We just have the doubles. Okay, so once again, okay, you just have to realize that you did, we did all of this exercise just to see how these expressions look like if we draw all pieces, including the resolvent, but we could agree on a rule. Okay? Instead, if I look at this wave function in the first order, I could have just said from the very beginning that it consists of 2 pieces. Let's call them now what they are. The A piece and the B piece. Where the A piece, okay, is simply resolvent Qn P0. But let's note one thing, okay? What survived from this, in this case, is just the one-body resolvent. Okay, so you're beginning to learn that we start with the resolvent, but our summation over n is gone. Okay, we just ended up with one-body resolvent here in the end. So this really is the one-body resolvent. Please really make sure that you copy this stuff, because that's very important now for the understanding of perturbation theory. Okay? There's a one-body part. That's all that survived. We started with sum over n, but there's no n anymore. There's one. Okay? And we know now that we obtained the expression, which is the sum over, what is it there? A qi over epsilon I minus epsilon a times the singly excited determinants. Okay? And as I said, we obtained this result by drawing the resolvent, but we could do it as follows. We could just say that this is represented by the following diagram. If you use Goldstone, that will be the diagram. AI, okay? Because this diagram has everything you need to get the right expression. The weight of it is 1, sign is 1, okay? The scalar factor is AQI. What you don't see there is the denominator, but we're going to accept now the rule that with all the external lines of MBPT diagrams, we associate the resolvent. Okay? Meaning that there is a denominator, and I will remind ourselves that we have one by putting that dashed line slicing through. Okay? So this is a reminder that there was a resolvent there. You just cannot, and and this really leads to the denominator. So in other words, we don't have to draw the resolvent. We could use a diagram like this and simply agree that lines that are sliced produce a perturbation theory denominator. And for the B part, okay, we have R0 Vn Phi0, but we just demonstrated, if you look at the calculation at the top, I think it's there, right? Okay. You see the n got, I didn't write it there, but we reduced n to just to n equal 2, okay? Because nothing else survived. Yes?
Why shouldn't this also have an anti-symmetry, or why can't I also draw a second?
Here?
So,
No, because if you exchange lines, it's going to be the same picture. Right? You could try it first. Right? You could try it, but but it's like, actually, I'll show it now, okay? So just give me a second. So we learned that only two-body resolvent survives, because V has 4 lines, which you have to connect to the lines of the resolvent. Please to register this information is extremely critical to understand quantum mechanics of many-body systems. And then you have, we proved that it equals 1/2 sum over ABIJ. What else do we have there? ABVIJ over the denominator. And then we have to multiply this by the doubly excited determinants, Phi, Ij, Ab. Okay? Oh my goodness. Go there, please. All right. Okay? And again, if we simply accept the denominator rule, then we could get this result straight from a very simple picture like this. Okay? We have 1V, so we're drawing 1V. We point all the lines to the left, because it's a wave function piece, okay? And we label it accordingly. That's all, okay? And you can see this diagram has everything that you need to learn this, to read this expression. Weight of it is 1/2, so you have 1/2. Okay, it's a Goldstone. Remember, it's a Goldstone, okay? And all line indices are free, so we're summing them over. Sign is +1 because there are no loops and no internal whole lines, okay? The matrix element is A, B, I, J. I've got it. All that I cannot see, if I use the original rules, is the denominator. But we're just going to accept now the rule that if you have external lines, okay, to the left of the leftmost vertex, you simply slice them through and you read the denominator. Okay? Simply you take whole lines minus particle lines, or energies of whole lines minus energies of particle lines. That's all. And then the double excited terminal, obviously you see it. You remember, each open path produces an x dagger x pair. So x dagger A, xi, x dagger B, xj, that's the double excited terminal, because we're reckoning phi0. We're done, you see? We don't need resolvents, really, it seems. Okay? That's the sort of message. Now, returning to your question, you see, there's no, because if I try to exchange lines, say I and j, that's the same picture. Okay? They are all free, that's why. Okay? So we don't have to do it. Of course, if you wanted to use Hugenholz, you could do it. I didn't do it, but I guess you all see this, that if the Hugenholz for it would be this. Okay? So let's maybe not, I guess, run circles around ourselves, right? We already know what would that be, right? This is Goldstone. This would be the corresponding Hugenholz. Okay, and you would rewrite this expression in a, okay, let's put that g here maybe. You would simply get 1 over 4, not 1 over 2. Okay, you would get a summation over a, b, I, j. You would get the anti-symmetrized matrix element. Okay, you would get the same denominator. You're slicing the same kinds of lines. Okay. And you would end up with a double excited determinant, okay? I should do that then. Yeah, I don't know how to do it. Okay, thanks. I'll write it, okay, I'll put it up in a second. Trying to do this. I, J, A, B, well, you know what it is. Okay, this and that, okay, how it works, right? Okay, so, and of course you can see that, I hope that you see that this is all equivalent. If you use anti-symmetrized, you have 1 over 4. If it's non-symmetric, it's 1 over 2. Because anti-symmetrized matrix element has 2 matrix elements in it, okay?
We're summing over all of them.
You always sum over all of them. See, MBPT is easy. MBPT is not like some other theory. Kappa is more complicated. It has fixed indices. Here there are no fixed indices at all. Alright? So no worries. You just sum over everything. Right? So never have to worry about any of this stuff that you have to worry about sometimes when you talk about fixed indices. Okay, so that's what you end up with, okay, for the wave function. Alright? You can, somehow it looks like we can get away with the resolvents. We don't need to think about them. We just have to accept the new rule. Okay? The denominator rule, associate denominators with lines you're slicing through with the right power. So, you can't forget about the resolvent. You always have to remember, if the resolvent came with a square, you would square the denominator. Okay, so you have to always register what powers of the resolvents are in various places. Okay, that's why I'm still drawing these dashed lines with these circles. Okay, just as a reminder. Okay, if you get really experienced, you probably don't have to do this, and eventually we're going to learn linear cluster theorem. We're not going to see powers of the resolvent anymore. At some point. Okay, not yet. All right, and for maybe as a reminder, because now I would like to, I guess I should finish soon. So let me just remind you that for the energy, we still have the results there, so maybe I should actually leave it there. We have the results for the energy over there, okay? So now we have the MBPT2 for the energy and MBPT for the wave function in their full glory. We've learned that we don't need perturbative denominator, we don't need resolvents to obtain these results because we can agree on the additional denominator rule, okay? And we can also interpret these results. So before I have to finish in a few minutes, so let me give you maybe a general explanation, because I don't want you to feel that this denominator rule is something that we can only prove by the examples. Okay, I don't like that notion at all. I like proving things here. And that means that let's understand why there is such a rule in MBPT considerations, okay, in general. So think of general order. General order expression has a following structure. There is a resolvent, okay, in some power. I'm going to call it M, okay. Then there is a perturbation. Then there is a resolvent again, right, in some power, maybe N. Then there's another perturbation, and you keep going like this. And you keep going like this maybe on the left, right? That's how the sort of middle of any perturbative expression looks like, okay? The only difference is that for the wave functions, you stop with W and Phi0 here, and W and Phi0 here. For wave functions here, you stop with the resolvent, okay, in some power. Let's sketch, now I'm going to be sort of doing the schematics rather than details, right? So, So what you see for this resolvent is a picture that, according to our schematics, what resolvents are, looks like this. Okay, I'm not going to even label it. We know there are particles with whole lines in them, right? We're slicing through, and there is an mth power, meaning the mth denominator, the mth power of the denominator associated with it. Then W is one or two body, I don't know. Right now, for this consideration, I just draw a circle saying that's a W. Has 2 or 4 lines in it, okay? Actually, if there were 3 body perturbations, that would be fine. You know, all the analysis I'm going to give you now applies to any perturbation, okay, of any form. There's the next resolvent here, okay? And we're slicing it through. The power is n, so it's going to be n, if that's what it is. Then there's the next W, and you keep drawing like this. Okay, that's how every perturbation theory expression looks like. And your role is to form resulting diagrams from these pieces, right? So, remembering that here you have, you have P0 here, in the middle corresponding to this line. Okay, and you have also Phi0 here, corresponding to that line. Okay, and then you have the next one, and the next one. It depends how many you've got there, right? So, just if you think about it, well, in MBPT there are always these regions. I'm going to mark it here, okay? Between Phi0s. That's because MBPT is like this. Because of the resolvents, you have these regions. You have to fully contract here, in this region. So in other words, all lines between these two lines, okay, must be fully contracted because of the expectation value that you've got there. Okay? Is this clear to everybody? That must be true. Which means that there is an implication of it. One implication is that if I think about what happens to this W, for example, so it hits on these lines, then you continue these lines, you have to contract all the lines here, and then you continue. Which means that there always are lines between the W's. Because there is always a resolvent between the W's. And the resolvent has at least 2 lines at each side, okay? So there is an important consequence. When you draw resulting MBPT diagrams, you cannot draw diagrams that do not have lines between W's. Okay? No such diagrams are allowed. This is, that they would be allowed in any other calculation. If we didn't have these resolvents, we would have W times W times W times W. It would be that simple. Well, then you would, of course, have various diagrams, including those where there are no lines between the W's. But not here. In MBPT, so please remember now, it's extremely important. Because of this arrangement of operators, we have to avoid diagrams, I'll schematically sketch it here, that will look like this. Imagine, let's use Goldstone. Okay? So these blocks, like before in various classes, imply some sort of region of the diagram I don't care about. That's another region of it. You can't do this. Yeah? If this is W here and W here, you cannot have a diagram where there are no lines between the perturbation vertices. Why? Because there is always a resolvent between these. Okay? That means that there are always some lines. Sometimes, you haven't asked me this question, but sometimes students ask me the question, well, do I really have to connect, am I allowed, it's a question, and maybe you already have it in your mind. Am I allowed to connect these two lines together? Yes. Because if this is, say, 2 lines, or 4, say, let's see, if this is 4 lines, okay? So 4 lines will have to be fully contracted. But the resolvent may bring you more if there is more in it. So you can flow, essentially what you can do is like this. You go through, flow, of course some lines end up here. But some will continue. Eventually they have to stop somewhere. Okay? If it's an expectation value, they'll stop completely. If it's a resolvent, you end up with certain lines. Okay? So in other words, the fact that our vertices are up to 2 body doesn't mean that there are only 4 lines in each region. There may be more. Because you can connect them. We didn't see, you may wonder, well, so why didn't we see it in second order? Because there were just 2 W's. There are just 2 W's. You cannot have, if you look at this, I erased them now, right? But, if you have only 2, okay, you see it there, so, right? If you look at the second order, you see, I have 4 lines. I know that it's P0 on this side, so I have to connect fully here. No room for anything, right? Now I have 4 lines leaving here, so I have to close it, right? There is no room for a variety. But if you have high orders, you won't see variety. which allows you to actually have some lines will go into W's, some lines will continue. But they'll stop at some point if it's an expectation value, okay, with a W, or they will simply be left hanging as external lines of the leftmost resultant, okay? But this is not allowed. Okay, remember, so you don't draw all resulting diagrams naively. You remember the concept of admissible diagrams when I said this? Admissible diagrams here are diagrams that avoid what we call described as dangerous denominators. That's a term that is used sometimes. And our rules are consistent with that, because, you know, what would that be? I would have to draw a line here between and try to read the denominator. What would I end up with? No excitation, because I don't have anything in between, right? Empty space. So you would have to think of this. Phi 0, that would be the line, divided by kappa 0 minus kappa 0. Because there are no lines you're slicing through. You'll be divided by 0. That's a singular. It's a singularity. You know, resolvent is avoiding that. Resolvent always sums over n at least 1. So you don't have a phi 0 terminate. Because you don't have phi 0 terminate, okay, term like this is not allowed. Of course, it's singular. That would make no sense. So we're not doing this. We're not going to do that. Okay? We do not allow drawing diagrams with dangerous denominators. That's a rule. Okay? Other than that, so maybe I just summarize the rules now and finish this discussion. Okay? The summary of the rules is this. I don't think I have to write it. Maybe there's a sake. You know, I hope it's clear to you. Look. You construct diagrams from W vertices only. You look at your expression in any order, okay? You construct diagrams from W vertices only. 1 and 2 bodies, like we did, Q's and V's, in all possible ways. Okay? For the wave function, for the energy corrections, you have to close all the lines. For the wave function corrections, you have to leave external lines extending to the left, coming from the leftmost resolvent. Okay? But you do not allow diagrams, resulting diagrams, that have dangerous denominators. That is, you cannot draw a diagram like this one here, which has no lines between neighboring W's. Because there is always a resolvent between neighboring W's. So you cannot have a diagram that has no lines between the two W's. Okay? So in other words, when you draw diagrams, you actually will have fewer diagrams than normally allowed by having multiple W's. Okay? That's the simplification already. And then there is a modification to these rules. So in addition to the standard rules of diagrammatics that we already know, you know, the weights, the signs, the scalars, and all that, okay? And in addition to the fact that energy diagrams have no external lines, in addition to the rule that wave function diagrams have external lines extend to the left, okay? We have the rule of dangerous denominators, avoid them, not allowed, and you associate perturbative denominators read by slicing lines between W's. Okay? Like we did in those examples, right? You just look at what lines are between the W's, slice them through, okay? And read as follows. Whole line, energies of whole lines minus energies of particle lines in the denominator to the power that corresponds to the power of the resolvent which was there, which you just don't want to look at anymore. Is this all clear to everybody? That's how we'll be dealing with MBPT from now on. I'm not going to be doing this resolvent stuff anymore. I just wanted to show you how resolvent disappears. Okay? It doesn't disappear entirely, as you can see. It leaves us with MBPT denominators. And it also leaves us with this rule. That rule you would not discover if you didn't see the resolvent first. Okay? The rule of dangerous denominators. Remember, no dangerous denominators. Okay. So I will stop right here by just saying one obvious thing. I would like you to appreciate a little bit of physics of this, right? I guess it is all physics, but, or chemistry for chemists, okay? It's all the same, all right? Let's call it that way, all right? So, if you look at the wave function, I already said this. Wave function contains singles and doubles. Single and double determinants. No information about triples, no information about quadruples. So you're already learning. If you want to know what is the triples contribution to the wave function, you need to go higher. I'm sorry. That's the way it is. Of course, for pairwise interactions. Okay? Same with energy. Second order correction has only singles and doubles in it. This singles, that doubles. Okay? Doubles, you know, because there's a two-body resolvent here, one-body resolvent here, that's why you have singles. Okay? So if you want to know triples, you know what to do. Go to the next order, third maybe. Well, we'll see next time that that's not even that is not enough. You know, you're going to learn that if you want to learn about triples, you have to go to fourth order. Anybody in quantum chemistry who ever run any program that I can't use, okay, which is a disgrace to the community, and the program that I can use and develop called games, okay, well, that, if you know, then you're going to run MP4, and you know when you look at the output, it brings the triples MP4 with a T, okay. So this is a lesson for us. That, you know, one thing that, you know, that you don't see in CR, different determinants come in different orders. You learn now that singles and doubles are already present in the lowest order, but not triples. But actually, if we use Hartree-Fock determinant as a reference, Hartree-Fock orbitals, then Q is 0. Well, if Q is 0, no singles even. Another lesson for you. Okay? If you use Hartree-Fock theory as your reference, zero order, then the lowest order correction to the wave function brings you doubles, and the lowest correction to the energy brings you doubles. That should not be surprising. We have a two-body Hamiltonian, so of course doubles should show up as early as possible. But no singles. What's the lesson? If you want to learn about singles, you need to go to the second order wave function correction. Okay? And if you want to see singles in the energy, in a Hartree-Fock case, you need to go to fourth order. Imagine. What is this telling us? Singles are much smaller than doubles. See, there's already physics here. I don't have to do any calculation to tell you just that. If I use Hartree-Fock orbitals, singles are fourth order, doubles are second order in the energy. Everybody would agree that fourth order is less important than second order. Okay? That's why bulk of the correlation energy is in the second order, well, typically in quantum chemistry, about 70% of it, okay, of the correlation energy is in the second order if you use Hartree-Fock, okay, and singles and these other triples and so on, they are all in higher orders, okay, actually the fourth order, okay. So please remember, we're learning a bit of underlying physics, yes, and I'll stop right now.
Can we transition to the review?
Yes. So I'm done with this. Just remember this. So next time we'll simply continue with the third order and so on. So Nicole, I'm done for the official part. Okay, let's go informal now about our questions. Okay.